to be talking about here. So if you are interested, please take your seats. We have got some people tuning in from online, so hello to those that are watching this on playback later on YouTube. My name is Anna Freeman. I'm the Policy Director at the Clean Energy Council in Australia, which is the peak body for the renewable energy sector. And I'm very excited about this afternoon's topic because I think this is one of those issues that is in people's minds as we head towards the tripling of renewable energy across our energy systems. Can we power our economies, our cities, our homes, our schools, our businesses, our hospitals with clean power 24/7? What happens when the wind doesn't blow and the sun doesn't shine? That's a very common question by those that sometimes oppose the clean energy transition. Can renewable energy offer us the reliability and the security that we need? And are we sure that we don't need 24/7 baseload power from something like a nuclear reactor, for example? Well, 10 years ago, these questions may have seemed more theoretical than actual. But today, renewables are no longer the minnows of the electricity system. Globally, solar PV and wind have more than doubled in the past 5 years and almost doubled their share of generation between 2018 and 2023. And the same is effectively true for Australia. We've gone from around 16% renewables in 2015 to over 40% in late 2024. And we're on our way towards around 48% by the end of next year on the electricity grid in Australia, based on what is under construction today. And by 2030, of course, all the Australians in the audience will know this, but Australia aims to achieve a target of 82% renewables in the power system by 2030. So what is involved in us getting there? What are the technologies and the smarts involved in moving from the old guard of large synchronous coal and gas-fired power stations to a fleet of wind and solar supported by energy storage? Is it feasible to achieve a power system operated at very high levels of renewables, if not 100% and beyond? That is the discussion that we will be having today. It won't surprise you to know that I have a view on those questions already, but that doesn't negate the fact that it's a challenging issue and there's a great deal of complexity in terms of how we are going to do it. I'm not an electrical or power systems engineer, and I'm sure that most of you in the audience aren't. Actually, I can spot a couple, so I might have to retract that. But we will be trying to ensure that this discussion today doesn't get impenetrably nerdy. However, I think we would all like to understand the issues better, as it's at the heart of the public's trust in the clean energy transition. I'm delighted to say that I have assembled an A list of speakers to address these questions today. I really mean that in the full sense. We have the people that you want to answer this question joining us today. To get us started, we are actually going to begin with a pre-record video from a person who has made quite a name for himself over the past 20 or so years as an advocate of water, wind and sun getting the job done. That we can power our entire energy systems, so not just your electricity system, but your energy system as a whole, on renewables. In 2008, he carried out a review of proposed energy technologies to address air pollution, global warming and energy security, and he concluded that water, wind and solar, which he refers to as WWS technologies, resulted in the greatest benefits. And in 2015, Mark Jacobson and his group of co-authors published plans for all 50 states and a continental US-wide grid study assuming 100% water, wind and sun. And that paper earned him a prize from the National Academy of Sciences for outstanding scientific excellence and originality. just this year he has a well-thumbed edition you can see in my hand here of No Miracles Needed, How Today's Technology Can Save Our Climate and Clean Energy, our clean air. So we are going to start with a presentation by Mark, and then we will move into a panel discussion. Let's hit it.
Good afternoon. Thank you for having me. I'm very pleased to be giving a presentation in the Australian Pavilion. I'm going to be sharing my screen right now, so just hold on one second. Okay, so I'm going to talk about how we can transition the world to 100% clean renewable energy and storage for everything, and why we do not need miracle technologies to accomplish this. First, I'm looking at this from three problems, point of view of three problems. One is air pollution causes about 7.5 million premature deaths each year, costing the world on the order of $30 trillion per year based on statistical cost of life. Global warming is obviously a rising problem, and it's estimated to cost on the order of $30 trillion per year by 2050, and we can already see the impacts of it. Fossil fuels are also limited resources. They will run out at some time, and that will result in energy price instability, economic instability, political and social instability, and that is a major energy insecurity problem. There are many other energy insecurity problems that have to be addressed simultaneously. Anyway, these three kind of problem categories are drastic and require immediate solutions. So our solutions during the past 15 years have been pretty simple. Electrify everything and provide the electricity with clean, renewable energy. So if we think of energy as four major types of sectors, with electricity/heat is one, transportation, buildings, and industry. Well, let's start with transportation. We would go primarily to battery electric and hydrogen fuel cell electric vehicles, where the hydrogen is produced from clean, renewable electricity, and that's for all ground, marine, and air transport. For buildings, we'd go to electric heat pumps for air heating, water heating, air conditioning, clothes drying, the heat for clothes drying, and also washing, clothes washing, and dishwashers even. We go to electric induction cooktops instead of gas stoves, LED lights, energy efficiency, more insulation. Heat pumps, for example, use 1/4 the energy as combustion heaters. For industry, we'd go to electric high temperature processes like electric arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, electron beam heaters, heat pumps for lower temperature industrial heat. And we provide the electricity in all cases with just onshore and offshore wind, solar photovoltaics on rooftops and in power plants, some concentrated solar power, geothermal electricity, hydroelectricity, tidal wave power, and there will be some direct heat needed that we can get from solar heat and geothermal heat. Because the wind doesn't always blow, the sun doesn't always shine, and by the way, wind and solar will comprise about 90% plus of the solution. And they're intermittent, so we do need electricity storage, but we also need heat and cold storage and some hydrogen storage. So there are many existing electricity storage options available. The largest in the world today is hydroelectric power, conventional hydroelectric power. The second largest is pumped hydroelectric storage. Batteries are now growing significantly in Australia, South Australia in particular. Batteries are starting to grow in the US, in California and Texas. They each have more than 8 gigawatts and 32 gigawatt hours of battery storage on the grid. But there are also other technologies available: flywheels, compressed air storage, gravitational storage, and even green hydrogen used for grid storage when powered through a fuel cell. We'd also need cold storage and hot storage for heating and cooling. The most common type today is water tank storage for both hot and cold, ice storage for cold, for district heating systems, underground storage in soil through boreholes, and also water pits, aquifers. These are for district heating systems. Long-term, these are seasonal heat storage up to 6 months. And also building materials, when you have certain types of building materials that can store heat inside of buildings to keep their temperatures modulated. And then a new technology called fire bricks, which are basically kiln bricks that can be heated up to 2000 degrees Celsius, and they can be heated intermittently by wind and solar through resistance heating, and you can store the heat, blow air through the fire bricks when the heat is needed, and provide heat for industry. The fire bricks are estimated to be able to satisfy heat for 90% of all industrial processes. They cost 1/10 the cost of batteries per kilowatt hour of energy storage. Well, and also we'll need some hydrogen. Hydrogen will be for limited purposes, and it's all green hydrogen, ammonia production, steel production, and long distance transport and some grid electricity, but not for passenger vehicles, not for heating homes, not for combustion. So can we power the entire world with just wind, water, and solar and electricity and some small amounts of heat? And so we did studies across 149 countries, and then broke those countries into 29 world regions and did grid stability analyses in these regions. So if I give a big overview of the results here, in 2020, the end use power demand averaged over all those countries is about 12.6 trillion watts. This is the annual average end use power demand. That's expected to go up to close to 19 trillion watts or terawatts in 2050. However, if we electrify all energy, provide that electricity with just wind, water, and solar, an interesting thing happens. The energy demand requirements go down about 54%. And that's for 5 reasons. One is the efficiency of battery electric and hydrogen fuel cell versus internal combustion engine vehicles. Each battery electric vehicle uses about 1/4 the energy as a gasoline vehicle, for example, because batteries convert about 80 to 90% of the electricity in them to motion, and the rest is waste heat, whereas gasoline vehicles only convert about 17 to 20% of the energy in the gasoline to motion, the rest is waste heat. We also get about 4% efficiency or energy reduction due to the efficiency of electric industry, about 13% averaged overall energy sectors due to the efficiency of heat pumps. Then we eliminate about 11% of all energy worldwide, because that's how much is used to mine, transport, and refine fossil fuels and uranium, and we won't need that anymore. And then finally, about 6.5% end-use energy efficiency improvements beyond business as usual. So that adds up to 54% reduction in demand without changing our habits. Now, if we look at this graphically, this starts from 2022 to 2050. If we don't do anything, we go along the top line along the business as usual case, where we get to 18.9 terawatts of end-use power demand in 2050. However, if we electrify everything, provide the electricity with wind, water, solar, we go down those 5 shades of colors to the 100% WWS line at 8.6 terawatts. And then what's left is we need to supply with just onshore and offshore wind, utility PV, CSP, some solar heat, rooftop PV, geothermal electricity and heat, some tidal wave and hydroelectric power. So this shows an 80% transition by 2030 and 100% by 2050. However, given that if we can actually transition 80% by 2030, there's really no reason we can't transition 100% by 2035. In fact, we have 95 to 97% of the technologies we need right now to transition. What we don't have are the long distance aircraft, long distance ships, but we know how to get those either through a combination of hydrogen fuel cell electricity and some battery electricity, but mostly hydrogen fuel cell for long distance transport and battery electricity for shorter distance aircraft and ships. So this shows that the same transition at the endpoint, but an 80% transition by 2030 and 100% by 2035. And so we think we can power the world for all purposes by 2035 with just wind, water, solar, if we deploy technologies that we have available right now as fast as possible. And between 20 and 2035, the ones we don't have will be developed. So what's the capital cost to keep the grid stable across the 149 countries? So remember, we broke the 149 countries into 29 world regions and did grid stability analyses. Well, worldwide, it's about $58 trillion. And this is a worldwide Green New Deal to eliminate air pollution, the 7.5 million deaths, or 90% of the 7.5 million deaths per year worldwide, they're from energy, eliminate the emissions associated with global warming, or most of them, and provide energy security. In the US, it's about 5.7 trillion. China, it's about 14.6. Europe's about 5.1 trillion. In Australia, it's about $500 billion, or $500 billion. But what's more relevant is the annual cost of energy. Today, the world spends about $11 trillion per year on energy. That's expected to go up to about $16.5 trillion per year by 2050. But the health costs of energy in 2050 are estimated here at $34 trillion per year, the climate cost at $31 trillion per year, the total social cost about $81 trillion per year. However, if we go to WWS, wind, water, solar, we eliminate health and climate costs associated with energy, our energy costs go down 60%. because we have a 54% reduction in the energy use and another 15% reduction in the cost per unit energy. So there's a $10 trillion drop in the cost, in the annual cost of energy. And if we divide $58 trillion up front by $10 trillion per year savings, that's about a payback time of 6 years. So there's a 6-year payback time, 60% drop in the energy cost, and there's 92% cost in the social cost by going to wind, water, solar. And just to look at the cost per unit energy right now from IRENA, the International Renewable Energy Agency, they estimate fossil fuels, well, this is calculated worldwide in a weighted average, about $100 per megawatt hour. Utility PV, onshore wind, offshore wind, geothermal, and hydro are all cheaper. Now, how much land does this take up? Well, worldwide, this is new land. We don't need new land for offshore wind or tidal or wave power. We're not adding any new hydro in these plans. Geothermal is small. Rooftop PV does not take up new land. So it's really PV plus CSP. You need new land for what's called footprint. Then onshore wind, we have spacing between wind turbines that we'll need land for. So worldwide, it's about 0.5% of the world's land is needed to transition. Sorry, there should be 149 countries. And in the US, it's about 1.1%. In Europe, about 0.9%. But to put it in perspective, in the US, 1.24% of all US land is used for corn, just for ethanol for transportation. And ethanol for transportation only provides 4% of transportation energy in the US. And another 1.3% of land is used for the fossil fuel industry. So we would decrease land requirements from about 2.5% down to 1.1% in the US. Well, one more thing is, well, we did comparison. We already talked about the business as usual case and a wind, water, solar case, but there have been proposals to, instead of using a lot of renewable energy, just add carbon capture to existing fossil fuel and bioenergy stationary sources and use direct air capture to suck CO2 out of the air. So we did 2 additional simulations. One where instead of doing any wind, water, solar on a large scale, we just did carbon capture and direct air capture. In one of those cases, we used business as usual fuels to run the carbon capture equipment. That's the BAU-CC-BAU case. In the other case, we used wind, water, solar to run the carbon capture and direct air capture equipment. And just to give you some assumptions here, in the carbon capture cases, we assumed a 6.7% reduction in energy demand, just like in the wind, water, solar case, just due to energy efficiency improvements beyond business as usual. We assumed about 9.8% of remaining business as usual energy demand comes from wind, water, solar, just naturally. 2.3% comes from nuclear. And those sources are assumed to emit no CO2, although nuclear does have some CO2 emissions. Then 85% of the remaining business as usual CO2 emissions are assumed to be carbon dioxide, and the rest are like methane and black carbon, which aren't captured. And then carbon capture and synthetic direct air carbon capture equipment are assumed to be 80% efficient. IEFA estimates it doesn't estimate from data, 10 to 80%. 80% is the upper limit of the observed efficiencies of carbon capture. And then we need 25% more energy with this carbon capture and direct air capture. IPCC estimates 13 to 44%. And finally, we assume all carbon dioxide is stored, although in reality today, 82% is used for enhanced oil recovery, which causes 30 to 40% of the CO2 to go right back to the air during the operations of EOR, and another 20 to 80% due to the burning of the extra fuel. But we assumed it all, for simplicity, to be stored. So what are the results? Well, I show energy results, air pollution death results, carbon dioxide results, and total social cost results. On the top left is energy. We increase energy use. Well, there's the business as usual is the left column. Then the 2 middle columns are these carbon capture cases, and the right column is wind, water, solar. So in the carbon capture cases, we increase energy use because there's an energy penalty associated with carbon capture. On the top right, panel B, we have an increase of air pollution because we use more energy. And in the business as usual power and carbon capture case, you're actually you're polluting more because you're using more energy and it's fossil fuels. A lot of that's fossil fuels. So you have more air pollution deaths. In the wind, water, solar carbon capture case, there's a slight reduction because we're using a little bit less energy. Wind, water, solar case, we go to 0 deaths. In the third panel, we do get a reduction of carbon dioxide in the carbon capture cases, but we go to 0 with wind, water, solar. So if we look at the final result, which is the most important one on the bottom right, total social cost, you can see the total social cost of wind, water, solar is on the order of 1/10 that of in either of the carbon capture cases, which are only slightly lower than the business as usual case. So to conclude, climate policies proposing carbon capture and or synthetic direct air carbon capture will increase air pollution, carbon dioxide equivalent emissions, energy needs, and private energy costs, the social energy costs, by 9.3 to 10.7 times those of policies requiring 100% wind, water, solar. The conclusions apply to any level of carbon removal above zero. Carbon capture and synthetic direct air carbon capture may, in the limit, cause millions of unnecessary air pollution deaths each year and substantial climate damage in the short and long terms. As such, policies promoting these technologies should be abandoned. And finally, with regard to our 149 country plans, we calculated 28 million more long-term full-time jobs than lost worldwide, gained than lost. We'd require only 0.13% of the land for footprint, 0.38% for spacing, avoid about 7 million air pollution deaths per year, slow than reverse global warming. We can keep the grid stable throughout the world with 100%, and we'd reduce energy costs 60% and social costs 92% compared with business as usual. And here are some additional sources in case you're interested. Thank you very much. Appreciate your invitation.
I appreciate the round of applause for a man that's not in the room. I think he will appreciate that too. He is actually going to watch it back on YouTube. So thank you so much. I think you can agree with me that that is the most phenomenal and incredibly comprehensive piece of analysis that he has undertaken. So thank you to Mark for the incredible body of research that he and his colleagues have conducted. I'd like to now welcome up our panellists. I'm going to start with Pablo Heviakosh, Head of Renewable Energy Integration and Secure Electricity. Please make your way to stage from the International Energy Agency. Pablo, in his role, oversees integration of renewables in the power system, electricity security, power grids, electricity market design, focused on both emerging and established economies. He's an electrical engineer by training, holds a PhD in energy economics from the Technical University of Denmark. And I have to say your job description sounds very tiring, but Pablo did tell me earlier that he found it extremely exciting. Next, I'd like to welcome Julia Sauder, CEO of Long Duration Energy Storage Council. She is also the current chair of the Global Renewables Alliance, where she has been influencing and at a very high level, and I think is in part responsible for this tripling of renewable energy deployment commitment that was made last year. And the Long Duration Energy Storage is a non-profit organisation with more than 60 members operating in 20 countries, so it's a global role. Finally, a man who's probably known to some of the Australians in the room, Darren Miller, CEO of the Australian Renewable Energy Agency, an organisation that he has led since 2018 and which was established by the Australian government in 2012 to help support pre-commercial innovation in the clean energy sector in Australia, helping to drive down the cost of deployment of clean energy. I'm going to begin by just making a comment, which is that our conversation today is very much going to focus largely on the electricity sector. A lot of the material that Mark covered was much broader, but we're going to have a slightly narrower lens on the power system transition. My first question to the panellists is actually a reflection on what you have just heard. Mark has really made the case that it's technologically feasible to power the entire world on renewables. He thinks 80% by 2030 is possible, 100% by 2035. There's a clear case in terms of the energy productivity savings. Any reflections from the panel? Should I start with you, Julia?
It's great to hear from Mark, and it is possible, and I think that's what we're all here at COP really working together on, how to make the policies stick so we can actually start building and deploying more renewable energy. I look forward to working with him and the team on storage and how storage becomes part of the narrative. As you mentioned, last year we worked really hard with partners, the IEA and others, about getting the 11 terawatts of renewable energy by 2030, which is now 5 years away. So we have a huge commitment to make. In this COP, we're working on the 1.5 terawatt energy storage goal by 2030. We have, if all of these in the grids and the grid corridor, if all of these come to fruition, then we'll have a pathway to help achieve this roadmap. it's really important that both the cost and savings are noted. And so if we deploy 8 terawatts of long duration energy storage, which will help the renewables work 24/7 and decrease curtailment, this is $540 billion US a savings a year. So the whole cost aspects there are really important, just to see that when you really minimize land mitigation and you really have 100% utilization of your resources like wind and solar, geothermal, pumped hydro being used, it really is achievable. But again, it takes all of us to work on this together.
Pablo, what Mark presented was a little bit different from the IEA's long-term world energy outlook. Where does the IEA sit in terms of what that transition looks like? And does that mean that you don't think that this is possible?
So just to understand a bit, the IEA is an all fuels, all technologies organization. So we don't focus on particularly any one technology. And that means that when we're looking at, for example, net zero scenarios.
Closer to your mouth.
Closer to my mouth. Perfect. When we're looking at net zero energy scenarios, we're focusing not just on what is possible, because we know that our pathway is one of the many pathways that can exist to achieve net zero emissions by 2050, but a pathway that we think it is cost efficient, it is fast enough to be deployed, and that brings the advantages that we see across all technologies. Now, there are some commonalities that I would really like to highlight. And the first one is that we really see the power system as the big lever to decarbonize societies. The power sector today is really the heartbeat of economies. It's really driving not just economic growth, but it's driving access to essential services and human rights. At the same time, we do see the power sector as the first one to decarbonize. And by taking advantage particularly of renewables such as wind and solar, coupled with storage both in the short and long term, it really creates this beautiful enabling effect that allows you to move into other sectors, industry, transport, buildings, and reduce the emissions in that direction. So I think for me, that is one of the big parts. And we do see that the emissions in the power sectors peak quite quickly globally on a net zero compliant scenario, and that definitely it's possible. So that for me would be the focus of this comparison.
Darren, any reflections on what you've just heard?
So I think that what Mark presented illustrates that we are very confident that we have technical solutions to every challenge. So I would divide up the pathway to net zero into 2 aspects. One is we have a range of technologies available today that are more cost effective than fossil fuel alternatives. And for those technologies, and I would say wind, solar, lithium-ion batteries, electric vehicles, heat pumps are the obvious sort of big levers, if you want to call it that. It's really a question of coordination, policy and finance. And so there should be no barriers technologically to achieving high penetrations of renewables in those mature technology sets. It's just a question of collaboration, coordination, finance and policy. And that's not to say that's easy or solved. That's the hard part, and that's really what COP is about. It's about putting in place the policies to see those things put into place throughout the world. But then there's another set of technologies which are, we know we can achieve 100% decarbonisation, but these technologies are much more expensive than the incumbent, and they need a lot more work in research and development and piloting, government funding from the likes of ARENA and agencies like ours around the world. And so, you know, that has to cross another barrier and then be adopted through those other levers. But certainly the challenge is absolutely solvable technically.
And some of those that are under development and maybe are emerging early stages, how far off are they? Is this within the near term, within the medium term, or are these issues that might take 20 years to solve?
The way I'd like to answer that is it doesn't matter how far off they are, because if we start to get worried about solving that last 10%, 20%, whatever we want to say is that harder to abate, the uneconomic part, we're going to get confused and stop action on the stuff we know we can do. So we really have to say, not to dive into niche issues of how do we solve that final bit. We need to do that through R&D, but we actually have to have confidence that we have those other technologies that are mature that just need everybody to get on board and accept that that's the way to go.
Yeah, fantastic. Pablo, I'm going to ask you if you could give us a bit of a sense of, in terms of what's going on.
internationally that we can draw inspiration from and lessons from. Australia's not the only country that's trying to do this. We probably, I don't know if it would be fair to say that we are seeing one of the higher rates of sort of VRE, variable renewable energy. By that we mean wind and solar entering the grid. I don't know, where do we sit in terms of in this transition when we look at the international peers, and who can we learn from?
Thanks a lot. I'm going to build a bit on the analysis that we released a month ago, precisely looking at integrating wind and solar, where the question that we try to answer is really, first of all, what are countries doing today, and what are the lessons that can be learned. And indeed, Australia, first of all, is a country that has a marvelous amount of resources in terms of sun, in terms of wind, that can really facilitate their acceleration, and the targets that they have are ambitious but realistic from our perspective. They require accelerating still a bit at the speed at which we're deploying. But when I look at countries that maybe have certain similarities, I can see that some of them are moving even faster. And here, when people think very often about power systems with high levels of variable renewables, maybe their mind goes to Denmark quite often. And actually, I'm not going to talk about Denmark, because it's in a situation that is quite different to the one that Australia has. But I would like to think a bit about Ireland, actually. Ireland is a country that, while it does not have as much sun as Australia, it does have quite a bit of wind. But the similarity is that it has challenges because it's not an interconnected system. So it's an island with limited interconnection to other regions. At the same time, they've been increasing the amount of variable renewable energy that they're integrating into their power system at really blazing fast speeds. And this shows a couple of things. The first one is that when you're talking about really accelerating how much renewable energy, and particularly wind and solar, you want to have in your power system, there is a significant number of measures that you can find worldwide. Some of them are technologies, some of them are market design choices, some of them are planning policies, some of them are operational measures that are tried and tested. That for most of these, we don't need R&D. We can really start today without going into the known. Now, Ireland in particular is looking quite far ahead, and they have very ambitious plans towards 2030. But at the same time, they have a quite clear roadmap that indicates where these technical frontiers are, and an interesting plan to solve them. And when we look at some of the more challenging issues, when you have really high levels of wind and solar, questions about inertia, for example, we can see that even for solving those problems, the technologies that are needed, some of them batteries, some of them grid-forming inverters and converters, or synchronous condensers, and all of these electrical engineer things that you told us not to talk too much about, not to get too nerdy.
No, that's fine. Go for it.
They're here today, some of them are not completely developed economically, but they're not at the research and development stage. You have pilot projects, you have implementation. Many countries around the world are building synchronous condensers. So my message from this is that even when you look at a system that does not have a strong interconnection, you can see that there is space for ambition, and that a significant share of the solutions that you need to achieve it are there. The question is really about how to implement them. And just to explain a bit the graph.
Sorry to the other panelists.
Sorry for our panelists. This is time for your panel yoga session. What we did is we took a look at what are the typical challenges and solutions faced by different power systems, depending on how many renewables they have, wind and solar, but also depending on the particularities of their own systems. So we classify them from phases 1 to 6. Phase 1 really being a point at which you feel no impact at the system level from new deployments, all the way to phase 6, when you're really trying to achieve complete supply from wind and solar. And the first message is globally, most systems are in low phases, but the speed at which they're moving to higher phases is accelerating. And by 2030, we see a growing number of power systems that are what we call high phases, phases 4 and 5 particularly, taking advantage of the existing knowledge and existing technologies.
You can see quite a gap there, can't you, between the Australia and the in 2023 versus 2030 in terms of how far it will jump.
Exactly. It shows the ambition. It also shows that Australia is a big country, and that means that if you look at it regionally, for example, you could say that, for example, South Australia is at a higher phase, compared to the national level, indicating that there's some space to grow. And I'm so sorry for your neck right now.
You can go and sit in the front row if you'd like, Julia. I've just put up, in your latest, you've just put out a new report in September on the integration of wind and solar, which is really the key question. How are we going to do this? These are variable sources of generation. Can you just talk us through this phases sort of analysis that you did? And then I might throw to Darren and ask him if he can give us a bit of a sense of where we're up to at the moment.
Sure, with pleasure. So the starting point of this analysis is in a context of the tripling of renewable energy capacity, which we think is an excellent target and essential. Reminding ourselves that it's not just the capacity that will decarbonize power systems, it's actually energy. And we need to make sure that as capacity grows at an even faster speed, which is what we want to happen, we're able to transform this new capacity into energy that gets to citizens, to industries, and to all kinds of end-use sectors. And we had two questions. First of all, what kind of typical challenges do different power systems experiment at different stages? And which kind of typical solutions do these power systems implement? Now, if you look at the top left, I can describe it for you, sorry, but we have what we call phase one. And this is at the beginning when you're starting to build your first wind and solar PV assets. And the particularities here is that at the system level, there's actually no noticeable impact. And that means that really, it's pure benefit, basically. You can really take all advantage. As you increase the amount of variable renewables in your system, you start seeing more effects. For example, some minor impacts where you start to see that your demand, your net load curve changes a bit, to points in which you see that VRE, wind and solar, determine the operation of the power system. So you move to a modern way of thinking where you're no longer thinking a bit old school on you run demand just to fulfill, you run supply to fulfill demand, but you acknowledge that in the same way that we've been taught as engineers to deal with the variability of demand, we can deal with the variability of supply, because no power system ever operates in a flat manner. Now, in phase three is where we see a bit of a switch, which is basically in systems that are transitioned to high shares and to high quantities. And this is where you start seeing, for example, variable renewables like wind and sun reaching almost all of the demand at some points in time, and then further seeing significant surplus, volumes of surplus in your power system. And here is where we talk a bit more about power system transformation, where you really need to focus on having a modern approach to how you plan, operate, and finance your power system. So to summarize it a bit, what we learned is that on the early stages, which can get you quite far, to be honest, early is not really just infancy, you can take advantage of measures that are simple, that are cheap, that can be implemented gradually, and that will set you up to be thinking a bit of a more holistic and modern perspective as you move into the high shares.
Thank you. That's a great overview. Darren, I guess when I'm thinking, ARENA has got one of its pillars, it's got the renewable energy integration as one of your sort of areas of innovation that you're assisting industry with. What are the sorts of things that we are starting to see now as we've got higher rates of renewables in the system, and the issues that you're trying to solve and assist industry with? And some of the technologies that that's resulting in Australia?
Sure. So I think if we start at the rooftop and work up, that might be helpful for Australia. So we've just crossed over 4 million out of our 10 million homes having rooftop solar. I think it's over 30 gigawatts of rooftop solar. It's the largest generation source if you want to classify it as a homogeneous thing, which obviously it's not, it's geographically dispersed, but it's by far leading the world in terms of its penetration for a large-scale grid of rooftop solar. So what we're seeing in that market is an unabated price signal for homes to keep investing, because homes are exposed to a very high electricity price, which encompasses a whole cost stack of distribution, retail margin, etc. So homes have a continued price signal to invest in rooftop solar. Interestingly, that's actually if it isn't already, will cause an issue for large-scale solar, because it's pushing out the economics of large-scale solar. And so what we're then seeing in the large-scale side is some solar developers having said to me, and they may have said the same to you or different, and I don't know, but they won't necessarily invest in solar without integrated storage, because the economic case for large-scale solar is undermined through the vast amounts of solar we have coming onto the grid in the middle of the day. And in an energy-only market, which is similar to, say, Texas, for example, where the price signal is very acute at the 5-minute level, as a developer, you have to figure out your economics, and in an economic equation where that middle of the day is carved out, and sometimes, many times, actually negative pricing because of the credits available for renewable energy, that's the challenge. It's how do you penetrate through our 40%, as you said, going to 48% share of renewable energy.
So storage becomes essential.
So storage, there's an absolute price signal for storage to invest in batteries at the home, batteries on the grid, in the distribution grids, and large-scale batteries, and all of that is happening at some kind of scale in Australia. The issue of grid stability becomes a reality at this point for Australia. So grids are investing in synchronous condensers, which are very expensive machines that simply run and spin to provide an inertial mass if the grid needs frequency or voltage support. And that's fine. Like that may be the cost of doing business for renewables, but what we're working on at ARENA is looking at how to test grid-forming battery technology, grid-forming inverters. So we've invested in a recent round $176 million to fund 8 large-scale batteries to upgrade or essentially embed advanced grid-forming capabilities into those batteries.
What are they? Can you just give us a pithy little explanation?
It's a combination of hardware and software that essentially lets those batteries do the driving of the grid rather than being responsive to what the grid throws at it. So essentially holding up the voltage waveform, making sure frequency is at 50 hertz. All of those things were sort of done for free by coal and gas generation and hadn't really been thought of as necessary until we've got this penetration happening. But there's always a technical solution for these things, and that's what's the state of the art in Australia, is using these batteries and this technology to actually hold up the grid in the absence of any coal and gas. And that's a real great innovation if it proves itself out.
We haven't got any yet in the grid. Are they?
We have a few, but not enough for the market operator to get the confidence that it needs, that at scale the batteries can do that job. So it's really just a trial and demonstration phase right now.
Right. And how important do you think they'll be as we head towards 80%? Are they become a critical component?
I think it's going to be very necessary for the market operator to get the confidence to take coal out of the system, that these things prove themselves.
All right. We've also talked a little bit about the importance of storage from a sort of time-shifting perspective. Really now the most common technology is lithium-ion batteries, and we're seeing sort of 2-hour batteries being common, and increasingly that the duration is increasing to 4. I wanted to ask you, Julia, there is some concern that, you have a wind drought or cloud cover for prolonged periods, particularly in winter, it could be tricky. How large is the role for long-duration energy storage? And can you start by defining for us what is long-duration energy storage?
Sure, and thank you again, Anna, for the invitation to be here in this beautiful pavilion in Australia. It's gorgeous. And 8 hours plus is how we define long-duration energy storage. We look at 8, 12, 24, 48, 100, seasonal and ultra-seasonal. And we really can provide this ability, the inertia, the dispatchability, the base load with renewable energy to get that 24/7 continuous clean power. There are 4 families of long-duration storage. So there's the batteries that are in the electrochemical, but there are a lot of Australian battery companies that use zinc bromide from existing local resources. A bromine mine, there's other groups that look at iron or copper or carbon, and there's vanadium, there's zinc, there's so many elements. Then there's chemical, which is hydrogen, green hydrogen, and that could be ultra long. And then there's thermal energy storage, and a lot of these do not degrade over time. You can capture the sun and use it for heating or cooling in the winter. And so this is a very efficient process. And then there's the...
What do you mean by thermal storage? You're talking about like the fire bricks that Mark talked about? Is that what you're...
Yeah, exactly. Rocks, salts, recycled materials, way to just hold and harness. I mean, this technology has been around for hundreds and hundreds of years. But it's just now where there's a need due to market infrastructure, and now we have technologies that have been in labs that are now coming out to be part of the market.
The return to the dumb technology. It'll be a mix of the smart and the dumb.
And it's very cost effective. You have some capex up front, but over time, right now in certain markets, thermal energy storage is at parity with natural gas plants. So you can replace gas plants and coal plants with thermal energy storage, and you have the upskilling of the jobs and technical capacity. So with the right market criteria that Darren was speaking about, their long duration energy storage can meet about 40 different types of like ancillary services. We get the little buckets, but nothing really. I think there's like 5 of them that get credit in most markets. And the capacity investment scheme market that's being created, devised in Australia, is a great starting point to start to bring in more of these diverse technologies so customers can see the savings over time. And then, so I mentioned, thermal energy storage, I mentioned chemical, electrochemical, and then there's mechanical, the gravity, the pumped hydro. Then there's flipping pumped hydro on its head and looking at other aspects. There's compressed air, liquid air. There's using existing infrastructure. Paulo and I were talking about mines. There's a lot of mines in Australia that have been, kind of put aside, and you can repurpose mines as uses of battery storage and different types of gravity components. So there's lots of options that are out there and huge cost savings that comes with this. But we need more access to the marketplaces. There are technologies that are more innovative than others that we need to kind of, and Arena's given hundreds of millions of Australian dollars to a lot of thermal energy storage companies to deploy from sandboxes to really scale up to gigawatt factories. And this is also really important too, as a support to have. But I'd say in addition to the growth in Australia and the market signals, there's a lot of international interest of companies coming to Australia. And there's so many laws that have been changed to help really support LDES. One more thing about Australia is it's a leader in setting targets for long duration storage. Victoria and New South Wales, when you combine it together, is over 10 gigawatts of LDES specifically. That is such a strong market signal to have patient long-term capital to come and invest. And because what we've seen with the solar amount in Australia, the appetite and the support for renewable energy is so powerful. So it's exciting to see how renewables, superpower of Australia's leadership, is building this marketplace, helping show cost and savings, and showing how every industry is part of this, whether it's the ports, the mines, agriculture, hard debate sectors. The pairing of renewable energy and long duration energy storage is essential.
There's a bit of a view, I think, that's been potentially promulgated by the gas sector that the renewable energy sector needs gas. Does the arrival of these and emergence of these technologies mean that, in fact, that's not going to be the case? What do you think is going to happen?
Be the case.
And how does that? You mentioned that thermal energy was cost competitive now already with gas-fired power generation
in Europe.
Has it been deployed somewhere? Have you got?
Yes. So we have members that are in 22 countries, and in Europe, especially because natural gas prices are higher. Thermal energy storage competes today. They don't need subsidies. They're not asking for anything else. There's also a carbon price in Europe, which also helps the process. In the United States, there are thermal energy storage companies, but there are market restrictions. They can participate in the Texas energy-only market, but they don't get additional resource adequacy services or ancillary service in other markets. In some markets, they can't sell back their excess heat or power to the grid. If they were allowed to, it would also really help on implementing more thermal energy storage. Another area is islands. A lot of islands use backup diesel generators. They are being replaced today with thermal energy storage or even types of batteries. And that's at parity there too, because the cost of diesel and local fuel sources are so expensive. So around the world, there are a lot of opportunities for this cost savings by bringing long duration energy storages into the process. The problem is, again, the scale. We need to really get to the scale to bring more cost down.
Fantastic. We've got about 5 minutes for questions. Have we got any from the audience? Could you please introduce yourself?
Yeah, Matthew Warnkin, corporate carbon project developer out of Australia. The question to the panel is, looking at Mark's projections on energy demand, how should we be thinking about those demand projections in light of data centers and AI drive? So I appreciate any sort of commentary around that.
Pablo.
Talking about that.
Yeah, we're whispering a bit about that. I donated my microphone to the audience. It's a great question, and this is one of the points where we diverge a bit with the views that were presented. We do see a growth in electricity demand for a couple of reasons. I mean, AI is on everybody's minds and data centers, and that's part of it. I would also say it's where we see a lot of uncertainty. Like, we know it's going up, but the cone of uncertainty is quite big. But it goes way beyond that, because at the beginning I was talking about this enabling effect, the leverage that it can make. And that means more electricity demand. It means taking industries that are using low, medium, and even some of them high heat processes that are typically burning fossil fuels and electrifying them. And electrification means more demand. It means more electric vehicles, not just the fancy Teslas at your homes, but globally speaking, a lot of two-wheelers, three-wheelers, delivery vehicles, trains. We also have hydrogen, which has not been present so much in this discussion, but in some cases to abate hard-to-abate sectors and industries, you will see an increased demand for electricity to create hydrogen molecules that come from renewables, so low carbon. So we do see a growth in electricity demand, particularly, and I think that's one of the places where we see the biggest divergence on the up and down, and that is why we put so much focus on making sure that we meet this, first of all, quickly, securely, and affordable. And at that point is where it's really hard to compete with the economics of solar PV and wind in many places.
Anything to add, Julia?
No, we were both commenting on that earlier, because data centers is it 20% growth? Is it 8% growth? Because all of a sudden AI is able to kind of figure out how to be more efficient and effective. We need to do more scenarios, and it would be fantastic maybe for IEA and IRENA to do a scenario on taking gas completely off the system and looking at how AI data centers would then respond. And in addition to that, I think it's also really important. Many data centers have already deployed small-scale LDES and are looking at the benefits. In addition to heating or cooling, there's other attributes that need to be taken into consideration. So that there's much more here to unpack, and I think we need to have many more conversations about this.
One thing is clear, though: if we were to stay with the status quo in terms of the fossil fuel base, you would be seeing an even greater growth in terms of energy, given the productivity gains that are met through the renewable energy deployment in general. Any other questions from the audience? Yes.
Hi, thank you. My name is Max from the University of Oxford. My question is, I guess, mostly for Julia. In terms of long-duration storage, this is an emerging technology. What are some principles of electricity market design that can help make these technologies investable? And are there any examples of markets or jurisdictions that have done a really good job at this stage? Thank you.
Thank you for the question. And one thing that we're doing at the LDES Council is debunking the myth that it's all new. It's not. I mean, pumped hydro and some of the compressed air have been around for either 100 years or 20 years, but we have new innovative technologies. So how do we balance this diversity within LDES? And the market criteria has picked up in a couple areas. Australia's leadership of looking at how it can bring together the eastern side and the western side. Those are two different types of markets that Australia is really trying to decipher, and they're doing a great job of market signals and having a very open process to talk about. Pumped hydro is going to take 5-6 years to build, but a compressed air plant is going to take 1 year. So how do we send different market criteria signals? The United Kingdom, and we have a report just launched on giving case examples around the world of different markets. The cap and floor that was just introduced, that's another great tool. If you look at Chile and the amount of solar wind that was curtailed, mainly solar, it really sends market signals to create a new market for short, medium, and long duration. The Philippines has ways today in the marketplace to have long duration energy stores enter in. But again, we need to fix some of the market criteria. In some areas of the world, you don't have to create a brand new market. You just have to turn the dial a little bit so you can say, here's your short duration signals, resource adequacy. Here are your long duration signals, and here's the way that you can get, the black start, the inertia, the capability that come into play too. More than happy to talk with you more offline. But there are lots of examples, and we hope to see many more as we have the storage plant.
One last quick question from him. Oh, you had the same question. Well, that's all the time we have.
Can I add one small thing? Because that was a very good question, and I really liked it. So sorry for killing your timeline, but
all good.
I would say that some of the things that were mentioned, which I find completely agreement, follow one principle that we try to summarize, and it's really you need to get used to the idea that you remunerate all technologies based on the value that they provide to the system. And that means that today there's many values that are provided by batteries, by renewables, by long duration storage that are not being remunerated for that. Because we were used to having energy-only markets that you assume that everything comes together. So when you want to talk about stability, think about the service and accept any technology or service that can give you the stability. When you want to talk about adequacy and capacity, do the same. Instead of trying to preemptively determine who should be allowed or not to participate on this, because there's so much value that comes from these new technologies, and it will make the regulators and the policymakers' life easier to try to follow this principle instead of creating many little patches that are technology specific. Of course, support the technologies that need it in the nascent stages, but generally
But
speaking,
reward the market services that they provide.
Exactly.
Individually, yeah. Well, thank you everybody for your participation and engagement today. That's been much appreciated. I think the takeaway messages for me is this is highly doable for Australia. We might not have all the answers right now, but they're close if they're not here today, and we are all working on them. It does seem to me too that this transition is moving very quickly in a whole range of jurisdictions, not just in Australia, and there's a lot that we can learn from each other. Thank you so much to our panellists.